Is Taylor Hicks, and this is the motion of a falling object for lab number 2. Newton's second law, or the momentum principle, will be used to track and model the motion of a falling object that starts from rest. Newton's second law is applied here via the formulas final velocity equals initial velocity plus net force over mass times delta t, and final position equals initial position times average velocity times delta t. In this lab experiment, I will be testing this principle via the motion of a falling object, which will be a red small sphere, and here the object is not moving at a constant velocity, so net force will not equal 0. I began by recording the motion of a falling object, and I put it through tracker. You can see here I tilted the axes because the camera filmed it at a slight angle, so to get accurate data I had to tilt the axes here. Delta t here in this case is 0.033 because the camera works at 30 frames per second, and I used my own height to set this length scale. And we can watch this video seen here. As you can see, the point mass tool tracks the motion as it moves down the axes, and all the data is collected here. And so, more information on this ball after doing this tracker. The mass can be recorded as 0.1148 kilograms. The initial position is 3.78 e to the negative fifth, and in the x position, negative 2.25 e to the negative fourth. In the x position in 0 meters, and the initial velocity is 0 in the x, negative 2.41 in the y, and 0 in the z. Meters per second. I then took that data we got from the tracker file and I put it into a starter code for GlowScript to model this. Big changes that are very important for this are that the weight was negative mass times g times j hat, and then the net force is just the weight. This accounts for the weight being the only external force here, and we can see this in this code. As you can see, these are the changes that I made. And so, how does this compare to the observed data? When placed all the data points from the GlowScript code and the observed data, you can see that it's not a very accurate depiction of this motion, so we will be needing to add drag force. And then adding the drag force into GlowScript, the only changes that were made here were adding the proportionality constant, which is b equals 0.01, and the drag force, which is b times the magnitude of the velocity squared times j hat, and that includes the square of the speed, and then net force is weight plus drag force. And those are the only two external forces that act on this object as it falls. And you can see the position versus time and the velocity versus time graph for this code here. And then final charts, the expected versus observed position over time graph with the drag force. You can see it's a very accurate depiction of this motion. And then all three of these, the without the drag force, with drag force, and the observed motion, the with drag force is a much better depiction of what's happening here. An object reaches terminal velocity when the force of drag pointed up has exactly balanced the force of gravity pointing down. This means that the net force will be 0 and the velocity will be constant. This can be seen in every model of falling motion that was explored in this lab. Because each graph flattens out as time goes on, one can see the effects of terminal velocity on the falling objects. This is also the same when an object is thrown downwards rather than being dropped from rest. So what if the object was thrown downwards rather than being dropped? Would this change the terminal velocity of the object? In this case, the object would reach the ground at a faster rate than if it was dropped from rest, as it would reach terminal velocity much quicker than if it was dropped from rest. This can be seen through editing the GlowScript code from the falling object with drag force. So rather than having this be the initial velocity, we would set it to something much faster, like negative 10 meters per second in the y direction. And then this is the graph that compares the observed original when falling from rest versus if it was thrown downwards. And as you see, the blue line, which is when it was thrown, it looks like it is almost just a straight line, so it's already reached its terminal velocity, while the red, it curves before it reaches the terminal velocity, and then these two are parallel. So therefore, this collides with the x-axis much faster than the red line, which is when dropped from rest. Thank you.